Hey everyone, welcome back. Today we're diving into a groundbreaking intersection of AI and robotics. How large language models are revolutionizing multi-agent systems. Ever wonder how a team of robots navigates a warehouse or avoids collisions while delivering packages? It's not just about coding rules, it's about teaching them to learn, adapt, and collaborate. And that's exactly what this research is cracking open. Let's start with the basics. In AI, reinforcement learning works like training a dog with treats. The agent, the dog, tries actions, gets rewards treats for good choices, and learns over time. But when you have multiple agents, like a team of robots, things get complex. This is multi-agent reinforcement learning, MARL. The challenge: each robot must learn not just its own path, but also how to coordinate with others. It's like teaching a soccer team to pass the ball without tripping over each other. Now here's the problem. Traditional MARL methods are super slow. They require millions of trial and error, attempts to find optimal strategies. Imagine a robot trying every possible route in a maze just to find the exit. That's where large language models, LLMs, like Vicuna-7B or GPT come in. These aren't just for writing essays. They can reason, plan, and generate logical sequences of actions. The researchers behind this study asked, what if we let an LLM act as an expert planner for robots? Think of it like giving a team of robots a GPS that doesn't just show a route, but also predicts traffic jams and suggests detours. The idea is that when robots face uncertainty, like a complex environment, the LLM steps in to guide them. How does this work? Let's break it down. The system uses QMIX, a MARL algorithm that helps agents collaborate. But here's the twist. When the algorithm detects high uncertainty, like when robots are confused about their next move, it queries the LLM for a plan. The LLM, trained on vast text data, generates step-by-step strategies, like a roadmap for navigating a maze. The researchers tested this by comparing two experts, a classic pathfinding algorithm A and the LLM. Surprisingly, the LLM outperformed A in complex scenarios. Why? Because it could handle ambiguous situations better, like figuring out how to split tasks when multiple robots are involved. But wait, how do you know when to trust the LLM? The system uses ensemble networks to measure uncertainty. If the robot's confidence in their decisions drops below a threshold, the LLM jumps in. It's like having a backup GPS that only activates when your phone's map fails. So what's the big takeaway? This research shows that LLMs aren't just for chatting or writing code. They can be powerful tools for real-world AI. By combining the reasoning power of LLMs with MARL, we're one step closer to robots that can work together smarter, faster, and with less human oversight. Let's dig deeper. The team tested QMIX with different components. First, a vanilla version using an LSTM, a type of RNN. But the agent's performance was unstable, like a team with no strategy. They then replaced the LSTM with an attention layer, which acts like a spotlight, helping the model focus on critical details. This version showed better stability and performance. The real game changer: replacing the traditional planner A with Vicuna-7B. Here's how it works. When uncertainty spikes, the system asks the LLM for advice. The LLM, trained on vast text data, generates step-by-step strategies, like a roadmap for navigating a maze. This approach outperformed in stability and effectiveness, proving that LLMs can act as powerful experts in multi-agent settings. But it's not perfect. The study noted that Vicuna-7B sometimes produces invalid actions, highlighting the need for refinement. Still, the results are promising. Why does this matter? MARL is key for real-world applications like warehouse robots, autonomous vehicles, or even AI in games. Training these systems is tough, because agents must learn from each other while dealing with uncertainty. By integrating LLMs as experts, we're unlocking more efficient exploration and decision-making. The experiments also tested scalability. They ran simulations in different environments, like virtual mazes or traffic scenarios, and varied the number of agents. Why? To ensure the system works no matter the team size. Imagine training robots in a warehouse. One setup might have 2 robots, another 10. The goal? To ensure the system scales smoothly. The team also extended their approach to handle complex action spaces, real-world tasks with multi-step decisions, like a robot assembling a car part by part. This makes the system adaptable to anything from game-playing AI to autonomous vehicles. Finally, let's peek at the code. The project's structure is designed for clarity. The main folder, LLM MARL, acts like a toolbox. Inside, config stores settings in YAML files, like learning rates. Logger tracks progress, like a training diary. Utils, handy functions for tasks like converting data into tensors. Key files include QMIX, Pi, which ties everything together, and Mixer, Pi, a neural network that combines agents' decisions. The code even integrates LLMs like Vicuna-7B to guide planning, kind of like giving the system a seasoned coach. So what's next? This research opens the door to smarter, more adaptive AI systems. Imagine a future where robots don't just follow rules,